Good day. I'm David Gabriel Feliciano, and this is my final completion presentation for Transmission Media and Antenna Systems Laboratory. Here we will discuss about different types of antennas. And first and foremost, what is antenna? So, an antenna is the metallic structure that captures and or transmits radio electromagnetic waves. Antennas come in all shapes and sizes, from little ones that can be found on your roof to watch television, and to the really big ones that capture signals from the satellites millions of miles away. It is also called an aerial component of radio, television, and radar systems that directs incoming and outgoing radio waves. So, um, Antennas are usually metal that have a wide variety of configurations, from mast-like devices employed for radio, television, broadcasting, to the large parabolic reflectors used to receive satellite signals and radio waves generated by um, distant astronomical objects. The first antenna was devised by a German physicist, namely Heinrich Hertz. Here's the sample picture of Mr. The German physicist Heinrich Hertz. Yeah, there we go. And during the late 1880s, he carried out a landmark experiment to test the theory of the British mathematician, namely James Clerk Maxwell. Here's the sample picture of James Clerk Maxwell. Um, that visible light is only example of a larger class of electromagnetic effects that could pass through air or empty space as a succession waves. I have here with me the very first antenna that was invented. So as you can see, the antenna that was first invented was so very large compared to the antennas right now in our generation. So Hertz built a transmitter for such waves, consisting of two flat square metallic plates, each attached to a rod, with the rods in turn connected to um, to a metal space close together. So an induction coil connected to the spheres that cause a spark to jump across the gap, and a producing oscillating currents in the rods. So the reception of waves at a distant point was indicated by a spark jumping across a gap in a loop of wire. So the Italian physicist, namely Guglielmo Marconi, the principal inventor of the wireless telegraphy. So I have here the sample picture of Mr. Marconi. So constructed various antennas for both sending and receiving, and he also discovered the importance of tall antenna structures in transmitting low frequency signals. So in the early antennas built by Mr. Marconi and others, operating frequencies were generally determined by antenna size and shape, In later, antenna's frequency was regulated by an oscillator which generated the transmitted signal. So, generally speaking, more powerful antennas were constructed uh, during 1920s, late 1920s by combining a number of elements in a systematic array. So, just like the metal horn antennas were devised during the subsequent decade following the development of waveguides that could direct the propagation of very high frequency radio signals. So, we have here the various types of the many types of antennas. The first one is called dipole. The second one is called folded dipole, and the third one, the monopole, and the fourth one is the Yagyu-the parasitic array, which we're going to demonstrate later. How does it work? The fifth one is the phased arrays, and the sixth one is the loop antenna, and seven is the helical antenna. The next one is the turnstile antenna, and microstrip patch antenna, and the dish antennas or the satellite dishes. So, uh, monopole antenna, what is that? It is a one-fourth length wavelength fed at one end. So, fed with unbalanced feed line with ground conductor connected to the earth ground. In practice, it is usually requires an array of radials to develop a better ground plane, which is the Marconi antenna, Mr. Marconi's antenna. When used at low frequencies, the field should be vertically polarized, and antenna could be a tower. The tower is ground insulated and fed at a point above ground with a gamma match, and the impedance increases upward. So, dipole antenna. Dipole antenna, it is one of the most widely used antenna types in the half-wave dipole. So, the half-wave dipole is also called a doublet. It is formally known as the Hertz antenna. Um, a dipole antenna is two pieces of wire, rod, or tubing that are 1/4 wavelength long at the operating resonant frequency. So as I've said before, this is the antenna that Mr. Hertz was invented. So converting a transmission line into an antenna. So as we can see here, the transmitter, this is a what you call that? This is the source of ito yung pinagkukunan ng supply. So tsaka niya itatransmit sa transmission line, and magpo-produce siya ng inefficient radiation. So, the next one is the basic principle of a dipole antenna. So, actual antenna lengths. A dipole resonates best when it is approximately 95% of the actual wavelength length. So it is equated by 1 feet is equals to 0.048 meters. In terms of L-feet naman, it is equal to 468 per frequency. Uh, um, s- 468 per millihertz. So the dipole hung vertically is closest to an isotropic radiator. The bottom of the dipole antenna should be at least one half a wavelength of to the ground. So conical antenna. A common way to increase bandwidth. Excuse. A common way to increase bandwidth is to use a version of the dipole antenna known as the conical antenna. So the center radiation resistance of a conical antenna is much higher than the 73 ohms that is usually found when straight wire or tubing conductors are being used. So the primary advantage of conical antennas is their tremendous bandwidth. They can maintain a constant impedance and gain over a 4:1 frequency range. So, conical antenna and variation. This is the basic principle of a conical antenna. So, as we can see here, this is the conical expansive, this is the bow tie flat, and this is the what you call the grid or flat plate. Um, that is two-dimensional cone equally effective. Next one is the antenna beam width. Um, as we can see here, the basic principle of a antenna beam width is uh, much as like a cardioid microphone. So the signal comes in here and here. So parang ito lang yung parang pinaka peripheral niya na nasagap na signal. Sa kabila naman ito, sa gilid wala. So folded dipole antenna. Same length as a one half wave dipole and parallel conductors joined at each end, separated by an appropriate spacing. So a 300 ohm radiation resistance, even though the current is same magnitude but out of phase with respect to the wire. In space, the currents are actually in the same direction due to folding of the antennas. So the next one is the folded dipole antenna again, and given the same conditions, a dipole and folded dipole radiate the same amount of power, and the current at the feed point is folded dipole is only half of the total current. So this one is the basic principle of the folded dipole antenna. So here, this is the one half wavelength, and this is the 300 ohms valence feed line that current pass through. So the next one, if the power is the same as the half wave of the dipole, and the current is reduced by half due to a folding, then feed point voltage must be doubled. So as we can see here, the equation here that is denoted, the power is equals to voltage times current, which is also equal to a twice of the voltage times multiplied by a current and over 2. So um, the result of a twice the voltage and the half current is a feed point impedance that is 4 times that of a dipole. So as we can see here, resistance is equals to voltage over the current, or the also known as the Ohm's law. Here, the derivative of the resistance is equals to um, twice the voltage over um, current over 2, which is also equal into a 4 times of the voltage over the current, and is equal to 4 times of the resistance. So next is the vertical monopole. Um, as you can see here, parang ito yung pinaka opposite ng folded dipole. Di, di ba yung kanina, yun sa folded dipole ay parang cardioid microphone na merong nakalagay dito sa magkabilaang side. Dito naman sa vertical monopole, isang side lang siya, and pag ganito yung pinaka basic illustration ng pagsagap niya ng signal. Monopole antenna. It is a 1/4 wavelength fed at one end. It is fed with an unbalanced feed line with ground conductor connected to the earth ground. It is in practice, it is usually requires an array of radials to develop a better ground plane. So when it is used at low frequencies, the field should be vertically polarized, and the antenna could be a tower. And the tower is ground insulated and fed at a point above the ground with a gamma match, and the impedance increases upward. So this is the basic principle of a monopole antenna. So ground plane antenna. What is ground plane antenna? It can use a counterpoise system of radials cut to a 1/4 wavelength to develop ground plane elevated above Earth. If used in a mobile application, the roof of the vehicle can serve as a ground plane. So at a low frequencies, a whip antenna can be used with a loading coil. So this is the basic principle of a ground plane antenna. As we can see here, ground plane antenna has a feed line that is connected to the ground. And the what you call this? The angle of receiving signal is 1/4 over 1/4 times lambda. So loop antenna. Typically, it is a receiving antenna. It uses an air core with radiation in plane of the loop. A ferrite core loop stick is also used typically in AM receivers, in AM radios. So radiation is in the same plane as the loop but broadside to the loop stick. So it can also be used as a coil in the radio frequency tuned circuit. So this is the basic principle of a loop antenna. As we can see here, this is the air wound and this is the ferrite core loop stick. So the maximum radiation here in air wound circulates inside, while the maximum radiation in ferrite core loop stick, uh, it circulates in air, in free space. So 5/8 wavelength antenna. Application as a mobile or base station antenna. It is also a omnidirectional response in horizontal plane. So the advantages is realized in the concentration of low angle radiation in horizontal direction. It does not require as a good ground plane because its feed point impedance at 5/8 wavelength is higher, therefore the lower current. So the impedance is lowered to the match 50 ohm feed line by matching section. So the next one is the helical antenna. Um, from the word itself, helix, it is a spiral antenna. An example of a 1/4 wavelength dipole shortened into helix or rubber ducky for handled transceivers. It is typically several wavelengths long and use it with a ground plane. So the circumference is half wavelength and turns are quarter wavelength apart. So the application uh, here is a very high frequency satellite transmissions, or what you call cross polarization. So this is the um, basic illustration of a helical antenna. As we can see here, we have spiral cord here, and this the coaxial feed line, which is na ipapasok yan dito. And dito yan nakalagay. This is the plane reflector, and this is the coaxial feed line. And the maximum radiation circulates over there. The next one is the long wire antennas. Long wire antennas, maraming klase ng long wire antennas. The first one, the one wavelength. So one wavelength, as we can see here, ganito yung orientation ng pag-receive ng signal. The next one is the two wavelength long wire antenna. May dalawang bali may apat siyang orientation ng pag-receive ng signal. And this the dalawa sa magkabilang side. The next one is the three wavelength antenna. Sa kabilang side, three orientations of receiving signals, and the other side is 3 also. The last one is the 4 wavelength antenna. Sa kabilang side, sa kabilang side, 4 orientations of receiving signals, and the other side is also 4 orientations of receiving signals. So, this cone antenna, wideband is to 10:1 range. It is a omnidirectional in horizontal plane. It is also a vertically polarized. Its gain is similar to a dipole, but the impedance approaches up to 50 ohms. The application here in this cone antenna is the RX scanners antenna for a very high frequency and the ultra high frequency antennas. It can also be used for a TX. So the parasitic array Yagi-Uda. So array antennas can be used to increase directivity, and parasitic array does not require a direct connection to each element by a feed network. So the parasite elements acquire their excitation from near field coupling by a driven element. A Yagi-Uda antenna is a great example of a linear array of parallel dipoles. So the basic Yagi unit consists of three elements. The first one is the driver or the driven element, and the next one is reflector, and the last one is the director. So Yagi-Uda develops an end fire radiation pattern. So optimum spacing for gain of a reflector, a driven element is 0.15 up to 0.25 wavelengths. So the director to director spacings are 0.2 up to 0.35 wavelengths apart. So reflector length is typically a half wavelengths or 1.05 that of the driven element. The driven element is calculated at resonance without a presence of parasitic elements. So the directors are usually 10 to 20% shorter than at resonance. So this is the basic principle of a Yagi-Uda antenna. As we can see here, this is the reflector and driven element, and this is the director's section. So the direction of maximum propagation goes here. So Yagi-Uda antennas is related to boom length and number of directors. The max directivity of a 3-element Yagi is 9 decibels or 7 decibels. So element ya So the max directivity of a 3-element Yagi is a 9 decibels or 7 decibels. So the addition of directors up to 5 or 6 provides significant increase in gain, and the addition of more directors has much less impact on gain. So increasing N from 3 to 4 results in 1 decibel increases. Adding a director to go from 9 to 10 presents a 0.2 decibels gain improvement. So adding more reflectors has minimal impact on gain. However, does impact on feed point Z. Feed point impedance and the back lobe. So this is the another radiation pattern for 8-element Yagi wood antenna. So metal booms can be implemented because the voltage is at zero midway through the element. So the other factors that affect resonant lengths, a comparatively large boom will require parasitic elements to increase their length, and a length to diameter ratio of the elements. So here is the example of a 7th element Yagi-Uda antenna. As we can see here, we have here the reflector section, the driven folded dipole section, and the director section. Here, this is the a log periodic dipole array. So before we discuss another computations for Yagi-Uda antennas, um, we will demonstrate the antenna. So here is the example of a Yagi-Uda antenna that I made from aluminum scraps. So now we will demonstrate this antenna and test this in a television. And let's see that this will amplify and receive signals channels. So as we can see here, there's no signal because it is not connected already. So now we will connect the Yagi-Uda antenna to test uh, na makaka-receive siya ng signal.
For some, he may seem as someone who is strict, brash, and authoritative.
So now as we can see, the Yagi-Uda antenna is working.
Despite the tough guy persona, he knows how to.
Here another channel, channel 5, minor tweakings to amplify a good signal. So yan sir, kita po natin, gumagana po siya. Channel 7, yan malinaw, mas malinaw. Channel 11, medyo mahina po yung reception. But it can amplify and receive a signal. So that's it. The channels na nare-receive nitong Yagi-Uda. Maraming channels. 7 channels. So, um, na-demonstrate natin na that kind of antenna, Yagi-Uda antenna, um, will amplify and receive signal channels, 7 signal channels actually. So now we will discuss uh, the other computations of the Yagi-Uda antennas. The first one is the time is equals to time constant. The time constant is equals to um, d distance 1 over distance 2, and is equals to distance over 2 distance over 3, and is equals to distance 3 over distance 4, and so forth. So D represents the spacing between elements elements and apex of angle closing them. So the D1 is the shortest. Um, the next one is the length 1 over twice of the distance 1 is equals to a alpha tangent multiplied by alpha over 2. And here time constant is equals to a length 1 over length 2. It is also equals to length 2 over length 3, and length 3 over length 4, and so forth, where L is represents is it is a respective element lengths. So alpha is the angle of the apex of tapered elements, and it is a typically 30 degrees. So here uh, we can see here the Yagi-Uda antenna and the log periodic. So this is the radiation pattern of the Yagi-Uda antenna, and this is the radiation pattern of log periodic. So the characteristics of the Yagi-Uda antenna, the polarization, its polarization is linear horizontal as shown, and the typical half power beamwidth 50 degrees multiplied by 50 degrees, and the typical gain is 5 up to 15 decibels, and the bandwidth of this antenna is 5%, or 1.05 is to 1. And the frequency limit, the lower frequency limit of this antenna is 50 megahertz, and the upper frequency limit of this antenna is 2 gigahertz. So the characteristics of a log periodic antenna is its polarization is also linear, and the typical half power beamwidth is 60 degrees by 80 degrees, and its typical gain is a 6 to 8 decibels 6 to 8 decibels, and its bandwidth is 163%, or 10 is to 1, and its lower frequency limit is 3 megahertz, and the upper frequency limit is 18 gigahertz. Remarks: this array may be formed with many shapes, including dipoles or toothed arrays. So here, this is the turnstile antenna. This is the basic principle of a turnstile antenna. So the first one is the geometry section, and the next one is the other one is the radiation pattern. So this is the geometry pattern of a turnstile antenna, and this is the radiation pattern of a turnstile antenna. So phased array antennas. So monopole array can the various types of phase array antennas are monopole array, collinear array, broadside array, and the end fire array. So we will see here the basic principle of monopole array. This the tower fed in phase, and this the 100-degree out of phase. These the radiation patterns for monopole antennas. The first one is the two monopoles in phase, and the other one is the two monopoles out of phase. So collinear array, it is a two or more half wavelength sections. So a broadside array, because the axis of the elements are along the same line. So half wave sections are linked by a quarter wave transmission lines. They develop a phase reversal to keep all dipoles in phase. It is also usually vertical and with an omnidirectional pattern in the horizontal plane with a narrow angle of radiation in the vertical. So multi-element broadside and end fire arrays. So broadside elements are spaced half wavelength apart, which is 180 degree phase shift, and in order to maintain a broadside presentation of the field the elements are fed out of phase, and the end fire elements are also a half wavelength apart elements uh, are fed in phase. So the radiation from all elements sum off to the end. So this the broadside array, and the other one is the collinear broadside comparison. And this a one of the example of stacked yagis na pinagpatong na yung na dalawang yagi with the antenna. So parabolic reflector, its gain is a function of parabolic reflector diameter, surface, accuracy, and illumination of reflector by the feed mechanism or focal point. Optimum illumination occurs when the power at the reflector edge is 10 decibel less than at the center. So FD ratios of 0.4 to 0.6 will deliver maximum gains. So a collimated beam of radiation will be produced. So this is the example of parabolic prime, and this is the parabolic. Its radiation pattern and characteristics. So it's almost the same. So parabolic reflector, G is equals to N times pi squared times D squared over lambda squared, where G is the power ratio with respect to isotropic radiator, and N represents efficiency, and the lambda is equals to free space wavelength. So theta is equals to 70 times lambda over D. It is the beam width, how you get the beam width. So the next one is F is equals to D squared over 16D, where F represents focal point The D, the D, the big D represents the dish diameter, and the smaller d is the depth from plane at the mouth of dish to the vertex. So this is the corner reflector and the Lundberg lens. This is the radiation pattern and its characteristics. So as we can see here, the characteristics of corner reflector, its polarization is field dependent, and the typical half power beamwidth is 40 degrees by variable. So it depends. Its typical gain is um, 10 decibels above feed, and its bandwidth is narrow, and the upper frequency limit the lower frequency limit of corner reflector is 1 gigahertz, and the upper frequency limit of corner reflector is 40 gigahertz. So remarks that typically fed with a dipole or collinear array. The next one is the characteristics of the Lundberg lens. So the polarization of Lundberg lens is field dependent, and the typical half power beamwidth of Lundberg lens is system dependent. The typical gain of Lundberg lens is also system dependent, and the bandwidth of Lundberg lens is narrow. So its frequency limit is just the same as the corner reflector. The lower frequency limit of Lundberg lens is 1 gigahertz, and the upper frequency limit of Lundberg lens is 40 gigahertz. Remarks that the variable index dielectric sphere. So, isotropic antenna. It is also known as an omnidirectional antenna. It emits the signal uniformly in all directions. In other words, at distance from the antenna in any direction, the transmitted signal power is the same. So although building a truly omnidirectional antenna is not feasible, this ideal antenna is frequently used to simplify range estimation analysis, as well as provide a reference point in comparing different types of antennas. So, anisotropic antenna radiates the energy fed into it equally in every direction in space. So, it is only an ideal model and cannot be built. So, real-world antennas can be characterized by their ability to radiate more strongly in some directions than in others. So, this is called directivity. When taking the efficiency of the antenna into account, this preference for a direction of radiation is referred to as gain. So, microstrip antennas. Uh, microstrip line. In a microstrip line, um, most of the electric field lines are concentrated underneath the microstrip. Because all fields do not exist between microstrip and ground plane, um, and we have a different dielectric constant than that of the substrate. It is less depending on geometry. So microstrip antennas, the electric field underneath the microstrip line is uniform across the line. So it is possible to excite an undesired transverse resonant mode if the frequency or line width increases. So it now behaves like like a resonator consuming power. A standing wave develops across its width as it acts as a resonator. So the electric field is at a maximum at both edges and goes to zero in the center. So microstrip discontinuities can be used to advantage to abrupt truncation and of microstrip lines develop fringing fields storing energy and acting like a capacitor because changes in electric field distribution are greater than that for magnetic field distribution. So the line is electricity longer than its physical length due to capacitance. For a microstrip patch, the width is much larger than that of the line. The fringing fields also radiates. So an equivalent circuit for a microstrip patch illustrates a parallel combination of conductance and capacitance at each edge. So the radiation from the patch is linearly polarized with the electrical field lying in the same direction as path length. So this the cavity back circuit fed slot, and this the guided fed slot. This the radiation pattern of cavity back circuit fed slot, and this the radiation pattern of the guided fed slot. So the characteristics of cavity back security fed slot, its polarization is linear and vertical as shown. Its typical half power beamwidth is 80 degrees by 80 degrees. So the next one is its typical gain is 6 decibels. The bandwidth of the cavity back circuit fed slot is narrow, and the lower frequency limit of cavity back circuit fed slot is 50 megahertz. The upper frequency limit of cavity back circuit fed slot is 18 gigahertz. So remarks that the feed line is sometimes separated from the radiator by a dielectric and uses capacitive coupling, which is large conformal phased arrays can be made this way. So the next one is its polarization. The polarization of guided fed slot is linear, and the typical half power beamwidth of guided fed slot, its elevation is 45 to 50 degrees, and the azimuth is 80 degrees. So its typical gain is 0 decibels. The bandwidth of guided fed slot is narrow. The lower frequency limit of guided fed slot is 2 gigahertz. The upper frequency limit of guided fed slot is 40 gigahertz. Remarks that the open radio frequency waveguide. So microstrip antennas. Um, this is how we compute the signals that receiving in microstrip antennas. So lambda is equals to lambda initial over the square root of the relative dielectric constant. So where the lambda initial is a denoted as a free space wavelength, and the relative dielectric constant. So L is equals to half of free space wavelength over the square root of relative dielectric constant. So the um, relative dielectric constant is equals to 0.5 or half of this equation, that uh, relative permittivity plus 1 quantity plus quantity relative permittivity minus 1 quantity multiplied by 1 plus 12h over W, or the wavelength, and it is powered to the negative 1 half, uh, where W is equals to 0.5 to the 2xl. So omnidirectional antennas. An omnidirectional antenna spreads the signal evenly in every direction of the plane. So directional antenna, a directional antenna forms a very narrow beam in a specific direction, and very little energy is directed elsewhere. If the beam becomes much wider, we will have a sectorial antenna. So spreads the signal. The sectorial antenna spreads the signal in certain angle of the plane. For instance, 45 degrees, 60 degrees, and so on. Often combined in a base station to provide 360-degree coverage. For instances, three sectors of 120 degrees each. So all antennas have a specific use case. In order to determine whether it is a directional or an omnidirectional antenna, is best, you need to know the basic functions of both. So an omnidirectional antenna radiates and receives the radio frequency energy equally, providing a 360-degree radiation pattern which allows connectivity in all directions. So the a directional antenna has a radius of around 45 to 90 degrees, focusing radio frequency energy and in a required direction, and limiting connectivity to that particular area. This can help also to overcome interference and multipath, providing better and more structured coverage. So directional and omnidirectional antennas in use within Wi-Fi AP applications. So antenna features. So these are available in different sizes, as well in shapes. As I've said before, the discussion, the small antennas can be found on the roofs to watch televisions, whereas the big ones are used to capturing signals using satellites. So how to select an antenna? So selecting the right television antenna for your particular television and location requires a number of things to be considered. So the next one is the type of antenna. What is it to be used for, satellite or terrestrial, along with the decisions. So about an internal or external antenna, an antenna gain, format, and many other things. So when selecting an antenna, there is a huge variety of antennas from form which to make a selection. So the first one is the satellite or terrestrial. Uh, it is a typically used on a sa NASA, sa mga weather forecasting systems, and one of the major na kailangan i-consider kung uh, when buying an antenna, kung indoor ba or outdoor. So the other major consideration that we need to consider is the gain or the directivity. So one of the key parameters of any antenna is its gain. So this the increase in what may be termed its sensitivity in a particular direction, the higher the gain, the greater its ability to pick up weak signals or to amplify weak signals. So when the gain is increased, the antenna also becomes more directive, meaning that it must be more accurately directed towards the TV transmitter. But also, this has the effect of reducing the level of interference that might be received from the other directions. So TV amplifier. In some areas, a television antenna amplifier may be needed to boost the signal. There are many different types of TV antenna booster or amplifiers that are available. One of the great examples is the Yagi Wood antenna that we demonstrated earlier. So bandwidth. So bandwidth is connected here in antennas. So bandwidth is a measure of how much information and a network can be transferred. So the volume of data that can be transported varies, impacting how effectively a transmission medium such as an internet connection operates. So generally speaking, the higher the bandwidth, the quicker a computer download the computer or the signal um, transmit to its host. So radiation pattern, as we've discussed earlier, the different types of antennas had the different radiation pattern. So the radiation pattern is defined as a mathematical function or graphical representation of the far field. Consequently, the terms of the gain pattern and electric field pattern, radiation vector pattern are used respectively. So two-dimensional radiation patterns. A pattern is isotropic if the radiation pattern is the same in all directions. Antennas with isotropic radiation patterns don't exist in practice but are sometimes discussed as a means of comparison with real antennas. So the directional radiation pattern for the dish antennas. So the third category of antennas are directional, which do not have a symmetry in the direction pattern. These antennas typically have a single peak direction in the radiation pattern. This is the direction where the bulk of the radiated power travels. These antennas are very common examples of an antennas with highly directional radiation patterns includes the dish antenna and the slotted waveguide antenna. So this is the example of radiation pattern usage. So beam width. Beam width is the angle form which the majority of the antenna's power, as illustrated on the radiation pattern main lobe, radiates. So it may be measured in the horizontal or vertical planes and is distance between 2 points where the power is less than half of the maximum. So analytical parameter, planning antenna coverage in a given area. So determining whether neighboring antennas will interfere with each other. So the assisting in improving the performance and communication links. So devising the deployment of networks within more one environment. One of the parameters to be considered is the development of the network mobility. So half power beamwidth, it is an angle between the half power points of the main lobe as measured at -3 decibels. So if planning an antenna array, the half power beamwidth will be the point where neighboring sectors cross over. So The first null beam width is the degree of angular separation from the main beam. So it is found between the null points of the main lobe of the antenna's radiation pattern. This measurement can assist in assessment of antenna interference. So what is the relationship between bandwidth and gain? So when the direction and the radiation distance of an antenna are known, bandwidth can also be used to determine the signal strength expected for an antenna. So gain is concerned with both the power efficiency and the directivity of the antenna, and therefore is also closely related to the beam width. So beam width and gain have an inverse relationship, decreasing the antenna bandwidth and it will increase the gain. So this is because by reducing the beam width, power transfer will be increased in a particular direction. So signal to noise ratio and beam width. As beam width relates closely to directivity and gain, alteration of beam width provides proportional changes in both these parameters. So in addition, the signal to noise ratio, the ratio of the signal strength to unwanted interference also changes accordingly. So if beam width is narrowed, gain and directivity will increase. This also increases the signal to noise ratio favorably. So for this reason, narrow beamwidth antennas are a prudent choice for a long distance transmissions. So polarization, this the one of the parameters to be considered in choosing a type of antenna, because all the types of antennas have a different polarization as we've discussed earlier. So vertical polarization refers to the oscillation of an antenna's electrical field on the vertical plane. So whereas horizontal polarization refers to the oscillation of the horizontal plane. The next one is the slant polarization. It refers to an electrical field that oscillates at a 45-degree angle to a reference plane. So, for example, it is a handheld and a direction finding. So, the other one is the circular polarization and the elliptical polarization. So, we are going to discuss here the reciprocity. So antenna characteristics like gain, beam width, efficiency, polarization, and impedance are independent of the antenna's use for either transmitting or receiving. So another way to state this is that an antenna's transmitting and receiving characteristics are reciprocal. So this is the wind load and the weather effects. So antenna's physical characteristics. So the antenna size and the antenna shape largely determines the frequencies that it can handle and how it radiates electromagnetic waves. So wavelength, we may recall from physics that wavelength and frequency of an electromagnetic wave in free space are related by the speed of light. Therefore, if a radio station is broadcasting at a frequency of 100 megahertz, the wavelength of its signal is a lambda is equals to 3.0 times 10 raised to 8 milliseconds over the 100 times 10 raised to 6 cycle per second is equals to 3 meters. So antenna gain, because an antenna is a passive device, the power radiated cannot be greater than the input power. So the ability of an antenna to focus electromagnetic energy is defined by its gain. And the gain of an antenna is a measure of power transmitted relative to the transmitted by an isotropic source. So effective radiated power. So effective radiated power is the gain of an antenna with respect to an isotropic radiator multiplied by its input power. So ERP, input power antenna gain. For example, a highly directional antenna with a gain of 7 has an input power of 1 kilowatts, and its ERP is therefore 7 kilowatts. So um before we end this discussion, I would like to add that over the years, many types of antennas have been developed for different purposes. And antenna may be designed specifically to transmit or to receive, though these functions may be performed by the same antenna. In general, it must be able to handle much more electrical energy than a receiving antenna. So, therefore, it may also be designed to transmit at specific frequencies. So, um, I think this I think we therefore conclude that antennas had a great impact in our generation. So thank you for listening. This is my um, this is my final completion presentation for transmission media and antenna systems for laboratory. So thank you.